done in this work, which has been done in collaboration with the General Institute, was to study the effect of an accretion torus on extreme acceleration spiral. So, one would like to use extreme acceleration spirals to detect the presence of matter which could be present in the galactic center. And basically, the most plausible candidate for this matter is given by an AGN accretion torus. So the question I want to try to answer is, can we see this accretion torus using gravitational wave observations coming from extreme acceleration spiral? To answer this question, we need some tools, which are basically the interaction, the processes which govern the interaction of the satellite black hole with the matter, the accretion disk. I will need to say a couple words about carriage dynamics. And finally, of course, I will need to set a model for the accretion torus. And in the end, if you follow me until the end, I hope I will be able to give you the answer to the initial question. So, you already know that extreme acceleration spirals are basically a satellite black hole having basically a mass comparable to the mass of the Sun, or almost 10 solar masses, orbiting around the supermassive black hole, which is thought to reside in the center of the galaxy. So the mass relation is very extreme because it's of the order of 10 to the minus 6. So for the first part of the trajectory of the small black hole, the trajectory is indistinguishable from a geodesic with laser sensitivity. But this lasts only for a few days or a few weeks, the so-called dephasing time. And after this period, you have to take into account the loss of energy and angular momentum through gravitational waves, and this leads to the spiral phase, which you heard a lot these days. One would like to use extreme acceleration spirals, as I said, to probe the geometry around the supermassive black holes. And the same is done using Earth, the artificial satellites orbiting around the Earth, for instance, like Champion Race. This can be used to probe the small irregularities of the gravitational field of the Earth coming from mountains or anisotropic distribution of masses and so on. I would like to do the same with space-time. And in particular to detect the matter which is present in galactic centers. So first of all, we need the orders of magnitude for this matter, which we think is we need the orders of magnitude for the sizes and masses of the accretion disks in AGNs. So as far as I know, the parameters and geometry of these disks are not very well known, but here I'm asking for your help because I'm luckily not an astrophysicist, but from what I heard and from what I talked with people doing AGNs, basically all we know is that the outer radius is the order of 10 to the 3, 10 to the 6 gravitational radii. The mass is at most equal to the mass of the supermassive black hole, but we don't really know. And the accretion rate is thought to be close to the Hamilton limit. So what are the effects which could affect an extreme acceleration spiral seen in space-time containing a Kerr black hole and an accretion disk? First, the first effect is the usual one, the self-force. That is the loss of energy and angular momentum through gravitational waves. And the self-force also has a conservative part, which should be observable by this and which should cause some periastral precession. In addition to this, in case you have this is the conventional process which affects the extreme acceleration spiral. This is present also in Kerr. In addition to this, one could naively think that the disk pulled on the satellite black hole, the gravitational attraction of the disk would be important because this disk could be rather massive, it could be of the same mass of the central supermassive black hole. However, if you do a simple Newtonian calculation, you see that the effect of the disk, you can compute using, for instance, a toy model, you can compute the periastral precession due to the gravitational potential of the disk, and you find that this effect is not visible by LISA unless the outer radius of the disk is less than 10 to the 3 gravitational radii. Basically, the rule of thumb is that LISA can detect at most a phase shift of one radian over its lifetime, one cycle over its lifetime. And of course, if you have disks which are very compact, you can see this effect. And the first attempt we tried to do this was in this paper However, what we are concerned with in this talk, well, you can have also another possible effect. You can think that the satellite is moving through the disk, so it accretes mass and angular momentum from the disk. So the spin, the satellite can be spun up until it can rotate very fast. So one could think that there could be a spin-orbit coupling or spin-spin coupling with the central supermassive black hole, but this could be possibly present also in normal extreme acceleration spirals around the cap black holes, and this has been shown to be negligible, for instance, by Leary in the case. But an effect which instead could be important is the hydrodynamic drag of the accretion disk on the satellite. And that's the effect I will talk about in this presentation. So the hydrodynamic drag was studied, the effect of the hydrodynamic drag was studied in normal galactic nuclei, that is, nuclei which are not active, which are very quiet environments, by radii using the so-called adios models for accretion, which is thought to be suitable for describing these objects. However, there are a number of works in which the effect of the hydrodynamic drag was shown to be important. And this work suggested that this could be the case also for the systems which we are considering in this talk. So the hydrodynamic drag consists basically of two parts. First part, which is due to accretion of matter onto the black hole satellite. If you accrete matter onto the black hole satellite, you transfer mass, energy, and angular momentum onto it. So you perturb the trajectory of the black hole. And the perturbation to the motion of the satellite is easily computed using conservation of energy and angular momentum. For instance, if you accrete mass to a black hole, you drag it down because you conserve the linear momentum. So you conserve the product of the mass and the velocity. So if you increase the mass, the velocity will increase. So that's why I call this a drag. Well, in our work, we describe accretion to the satellite black hole using the Bondi accretion rate, which in the Newtonian case is given by this expression. Well, our aim would be to do everything relativistically, but unfortunately for the accretion, Bondi accretion rate, there are no relativistic expressions because one needs to use hydrodynamic simulations to compute the relativistic version of this drag. And the numerical data are still too sparse to produce a fit. And of course, we need to compute this drag a lot of times during our work, so we cannot really do numerical relativity to compute this drag. And nevertheless, it turns out from the published data that the relativistic correction to this Bondi accretion rate are of the order from 5 to 25. And so the overall effect of the relativistic correction is to increase the effect of the matter which is present around the supermassive black hole. So in this sense, considering the expression for the Bondi accretion rate will only increase the effect of the disk. So this is a conservative assumption for our purposes. We then have a long-range part, which the astrophysicists probably know as dynamic friction, which has two equivalent, you've heard a lot about dynamic friction these days, so I'll try to be short. You can interpret dynamic friction in two equivalent ways. Either as deflection of matter which is passing far from the black hole and which is deflected by the gravitational field of the black hole, thus transferring linear momentum to the black hole. Or you can also think it as the gravitational pull of the fluid perturbations which are produced in the fluid, in the accretion disk by the satellite itself. So I'll try to explain this using a couple of figures which you've already seen. This is the first interpretation, which is the one which was usually used in the original derivation by Chandrasekhar in the 40s. So you have a star, for instance, moving in a sea of dark matter particles, or a star moving, or a massive star moving in a sea of stars with lower mass. So as the satellite is moving, particles are attracted by the big star, but meanwhile, the satellite moves on, the big star moves on, so the particles are gathered behind the satellite and cause the formation of a wake, which pulls the satellite back. And this is basically the dynamical friction in a collisionless fluid. if you have a collisional fluid, normal fluid with pressure and density and everything, you can have an alternative explanation. You can think of a particle initially in this position here, initially in the cross here, which is moving to the right until this position, which is indicated by a black dot. If the particle is moving at a speed which is less than the speed of sound, the area which is reached by the sound waves produced by the particle is a sphere centered in the initial position of the particle, which includes the present position of the particle. So the particle is here. This sphere here is the region affected by the gravitation, by the sound waves produced by the particle. So the particle feels in a non-symmetric pattern of density perturbations, which pulls it back. And the same is true if the motion is supersonic, because in this case the pattern of density perturbations is given by this by the Mach cone, this Mach cone pattern, which you probably know very well. So the particle after a certain time is here, and it feels all the density perturbations in this region. So the particle is pulled back in a much more efficient way if the motion is supersonic than if the motion is subsonic. This is dynamic of friction, and we treat dynamic of friction in this cartoon explanation. I use the Newtonian concepts, but we have relativistic expressions for dynamic of friction, so we can treat it at velocities which are close to the velocity of light. So the other tool, which I was mentioning in my introduction, are geodesics in a Kerr space-time. Because what we do in our work is considering geodesics, fixed geodesics in the Kerr space-time, and considering and averaging the effect of the disk over many orbits of the satellite black hole. So probably you already know that geodesics in Kerr can be characterized by three constants of motion. The so-called the energy, angular momentum, and the so-called Carter constant. And these three constants of motion can be remapped to quantities which are more familiar probably to astrophysicists, which are the latus rectum and eccentricity, which are defined in terms of the apoastron and periastron radius. And of course, in the weak field limit, these two quantities reduce to the Newtonian latus rectum and eccentricity. And we also need a third constant of motion, which basically depends on the Carter constant, which is the inclination of the orbit with respect to the equatorial plane. The interpretation of this constant as the inclination of the orbit with respect to the equatorial plane is exact in Schwarzschild, because in Schwarzschild you have geodetic motion is planar, so you can really find the inclination of the orbit with respect to the equatorial plane. And with some caveats, this interpretation can be transferred also to the case of Kerr geodesics. By convention, this inclination angle goes from 0 for equatorial prograde orbits to pi½ for polar orbits, and to pi for equatorial retrograde orbits. This is just the distinction between orbits with inclination less than 90 degrees are prograde orbits, and orbits with inclination which is more than 90 degrees are retrograde orbits. So what we do is to consider the effect of the hydrodynamic drag on the constants of motion E, L, and Q, derived using these expressions, the rates of change of the latus rectum and eccentricity and the inclination angle, and compare this effect, which is due to the hydrodynamic drag, with the rates of change of these constants of motion due to radiation reaction, that is the dissipative part of the self-force. Or if you prefer, radiation reaction is really gravitational wave emission. And for radiation reaction, we used some simplified treatment, which is usually called huge fluxes, which dates back to this paper by Jonathan Gare and Kostas Klampedakis, and these fluxes are just based on post-Newtonian expressions corrected with fits to numerical tubules data. So finally, the last tool I need is the torus model, which is basically the main ingredient of this of our treatment. So we want a torus which is over a curved background. So what we consider is a torus over a curved background which has a mass which is negligible with respect to the mass of the central black hole. And the other assumption we make is that the specific angular momentum, that is the angular momentum per unit mass, is constant, per unit energy basically is constant. And these two assumptions, well, they are simplifying assumptions, but they allow us to have an analytical solution for this torus. And in the end, of course, we will break this assumption because we will extrapolate our results to the case in which the torus has a mass which is even comparable to the mass of the central supermassive black hole. Although we consider, for instance, cases in which the mass of the torus is 10% of the mass of the central black hole, or in other cases in which it is comparable, as we'll explain in a while. So these tori, moreover, are stationary solutions of the relativistic Euler equations. So since we are in a stationary situation, we cannot accrete on the central supermassive black hole. And so we impose the accretion rating to the central supermassive black hole to be 0. And this again is a conservative assumption, because if we had an accreting torus onto the central supermassive black hole, the effect of the torus would be enhanced. If one makes this assumption, the inner edge of the torus basically coincides with the so-called mass shedding point of the torus, or what is called cusp in the terminology of these models. The outer edge of the torus, as I said, is taken to be a constant which goes from 10 to the 3 or 10 to the 6 gravitational radii, according to the case we are considering. Whereas the inner edge of the torus, by construction, is less than the radius of the innermost stable circular orbit, the so-called disk. So the radius, inner radius of the torus is very close to the horizon. The density profile, of course, is not constant in these models, and the density reaches a maximum at the point which is called center, and which has a radius which is larger than the radius of the disk. Finally, even the motion of the fluid is not Keplerian in these models, unlike some other disk models. And it is Keplerian only, basically, it's not Keplerian due to pressure gradients, basically. These pressure gradients are 0 only in two points, the center and the mass shedding point, that is the inner radius of the disk. So in these 2 points, both the disk fluid and the satellite are moving at the Keplerian velocity. So there is no relative motion of the fluid with respect to the satellite. And this basically makes the hydrodynamic drag 0, because the satellite is basically moving with the fluid as it was a piece of the fluid. So since it is a piece of the fluid, basically from the weak equivalence principle, it can feel an effect from the surrounding fluid. So in these 2 points, the center and the mass shedding point, the rates of change of the energy angular momentum with Hartley constant due to the presence of the disk are exactly 0. So summing up, our solutions are fully determined by 4 parameters. Well, we need an assumption. We need to impose that the inner radius is equal to the cusp radius. But once we've done this assumption, which amounts to choosing the accretion rate to be exactly 0, we have just 4 parameters: the speed and mass of the black hole, of the supermassive black hole, and the radius, outer radius, and the mass of the torus. The situation is even simpler, because if we change the mass of the torus, it turns out that the rates of change of the energy angular momentum scale proportionally to the mass of the torus. Basically, because if we keep the radius of the torus fixed, and if we increase the mass, the density changes proportionally to the mass of the torus, of course. And on the other hand, the rates of change of the orbital parameters due to hydrodynamic drag are proportional to the density. So the mass of the torus can be changed very easily in our models. So here are the results for circular equatorial orbits. Let me explain to you what these results mean. First of all, I should mention that these results are with very good approximation independent of the mass of the satellite, which I call small n. and of the mass of the central supermassive black hole, which I call big N. So here on the x-axis, you see the radius of the circular orbit expressed in gravitational radii. We are taking this radius to be positive for prograde orbits and negative for retrograde orbits. This is just a convention. Whereas here on the y-axis, I consider the ratio between the rate of change of the radius due to the hydrodynamic drag over the rate of change of the radius due to the gravitational radiation reaction. So this is basically the efficiency of the hydrodynamic drag. The torus I consider here is has a mass which is 10% of the mass of the central supermassive black hole. But if you want a different mass for the central supermassive black hole, if you want, for instance, to increase it by a factor of 10, you just have to multiply this ratio by a factor of 10. And that's why I have this scaling here in the label. The radius of the, I consider different radii for the torus. I consider a radius of 10 to the 3 gravitational radii up to a radius of 10 to the 6 gravitational radii. And I consider also two different spin for the central supermassive black hole. Either a black hole which is almost maximally co-rotating with respect to the torus, or a black hole which is almost maximally counter-rotating with respect to the torus. And as you can see, for instance, this is the case of 10 to the 6 gravitational radii torus. And in this case, the effect of the hydrodynamic drag is always negligible with respect to radiation reaction. But if you decrease, of course, the mass of the torus, so you can have cases, for instance, the blue curves, which correspond to a radius of 10 to the 3 gravitational radii, in which the effect of the hydrodynamic drag is dominant or at most compared with a gravitational wave emission, even at radii which are 20 gravitational radii for retrograde orbits, or 30 gravitational radii for prograde orbits. And basically, it's also possible to see that within 1%, the effect of the disk stays as the outer radius of the disk to the minus 1.5. We also considered generic orbits in impaired space-time, and we've considered the evolution of the eccentricity and found similar results to what people find on much larger scales. So we find that in general, the hydrodynamic drag tends to circularize orbits in the prograde case, or to increase the eccentricity in the retrograde case. But what I find more interesting is the evolution of the inclination angle due to the hydrodynamic drag. So this figure basically plots the base 10 logarithm of the ratio between the rates of change of the inclination due to the hydrodynamic drag and the rate of change of the inclination due to the gravitational wave emission. And the color code, plots represents this base 10 logarithm, whereas on the y-axis you have the latus rectum of the orbit divided by the mass, the central supermassive black hole. On the y-axis you have the inclination of the orbit. So this corresponds to an inclination angle of 0 corresponds to prograde orbits, and an angle of 180 degrees corresponds to retrograde orbits. This is done for an eccentricity of 0.1, but you can basically obtain the same results for any eccentricities. This is again done for a mass of the torus of 10% the mass of the central supermassive black hole. But if you want again a different mass, if you want to increase this mass to the mass of the central supermassive black hole, you just need to multiply this ratio by a factor of 10. So as you can see, even for a 10 to the 5 outer radius for the Accretion torus, you see that the effect of the inclination angle is comparable to the one of the radiation reaction up to down to a latus rectum of 30 gravitational radii. I should also mention that even an effect of the hydrodynamic drag, which is just 10% of the mass of the effect of gravitational wave emission, may be relevant for LISA, because the dephasing time scales as basically as this ratio, as the square root of this radius. So if the dephasing time between a waveform so we expect this effect, an effect if the dephasing time for LISA, for this orbit, is of orders of weeks, the inclusion of the hydrodynamic drag will increase the dephasing time only by a factor of the square root of 10, which is a factor 3. So one would expect to see this, to be able to see this dephasing LISA. Of course, one caveat, I'm plotting here outer radii which go up to 50 gravitational radii, but this is relevant only for a 10 to the 5 central supermassive black hole, because otherwise this this radius, an orbit with this radius is outside the LISA band. Moreover, I should stress that the effect of the hydrodynamic drag has different signs with respect to the sign of the gravitational wave emission, because gravitational wave emission always makes the inclination angle to increase, whereas the hydrodynamic drag always makes the inclination angle to decrease. So these two effects are qualitatively of opposite sign. So once again, one can change the outer radius of the torus. If one increases the outer radius of the torus, of course, the effect of the hydrodynamic drag becomes more important. What I plotted here is the orbits for which the effect of the hydrodynamic drag on the inclination angle is equal to the effect of gravitational wave emission on the evolution of the inclination angle. So for a 10 to the 3 outer radius for the torus, the two effects are comparable at a lato spectrum of 10 gravitational radii, which is relevant also for a 10 to the 6 central supermassive black hole. Once again, if you still increase the mass of the torus, all this value, the curve moves even closer to the central supermassive black hole. So, well, the fact that the hydrodynamic drag decreases the inclination of the orbit with respect to the equatorial plane is not surprising, because, as I said, it's rather intuitive that if the satellite is counter-rotating with respect to the torus will tend to make it co-rotate with it. And this amounts to decreasing the inclination angle from a value which is more than pi-half to a value which is less than pi-half. Moreover, even if the satellite is co-rotating with the torus, both the oscillations around the equatorial plane are damped, both because of dynamical friction, which is of course a dissipative effect, and because of accretion onto the satellite black hole. Because if we accrete mass on a black hole, and if we conserve the linear momentum in the theta direction, the velocity in the theta direction is decreased because of the conservation of the increase, because of the conservation of the linear momentum and of the increase of the mass. So the decrease of the inclination due to the hydrodynamic drag is basically independent of the torus model that we use. So the conclusions are that the hydrodynamic drag is probably not important with respect to radiation reaction in the very strong field limit of supermassive black hole. This is good news for when trying to look for gravitational wave emission by AGNs which are in the strong field region, because that means that we can use pure curtain plates even in the case in which an accretion torus with these characteristics is present. On the other hand, the hydrodynamic drag may be detectable by LISA in two cases. In the case of a 10 to the 6 central supermassive black hole and the comparable mass torus, if the radius is as small as 10 to the 3, 10 to the 4 gravitational radii. And in the case of a 10 to the 5 solar masses torus, what I meant here was in the case of a 10 to the 5 central solar masses black hole, central supermassive black hole, the LISA for a 10 to the 5 solar masses central supermassive black hole, one may be able to see also a torus which has a mass of 10% of the mass of the central supermassive black hole, even if the radius is rather large, 10⁵ gravitation radii. Of course, if one looks at orbits which are far away from the central supermassive black hole, orbits which have a radius of 30 gravitational radii, the signal's amplitude is decreased, so one needs a way to increase this amplitude. For instance, if one may imagine, one may hope to see an intermediate mass black hole spiraling into this system, or one may even think that since in event rate calculations one usually considers only the events which are very close to the central supermassive black hole, extending considering also orbits with radius of 30 gravitational radii may increase the inclination, may increase the event rate. So, and finally, the effect of the hydrodynamic drag on the orbit's inclination is qualitatively different from the effect of gravitational wave emission. So this could really be a smoking gun for the presence of the torus with the characteristics we have used in our investigation.